First of all, good afternoon, everybody. And I would like to thank Karen and the organizers of the TYC for organizing such a nice event. And we hope with this to keep the community together in this difficult time. So since I have only 20 minutes, I will start immediately. So today we are going to talk about graphene. But I'm not going to talk about the extraordinary property of this material, but I'm going to talk about graphene in suspension or dispersion. So we are talking about colloidal particles of graphene, which are suspended in a liquid. And my broad interest has always been, as a fluid mechanicist, to try to understand how graphene behaves in a liquid, how shear forces affect the motion and orientation of these particles, and how the shear forces can also deform the particles, potentially breaking them. Most of the work that I'm going to tell you about has been started in Queen Mary. All the ideas really started in Queen Mary University, where I was employed. And recently I moved to TU Delft, but still part of my research group is in Queen Mary University. So first of all, why I chose the name nano-hydrodynamics. So you may know that this name actually comes as a temporal evolution of the field of colloidal microhydrodynamics, which is a field that really started, particularly in the UK, in the 60s, thanks to the work of George Batchelor, Cambridge University, who really laid the foundation, mathematical and theoretical foundations for this field. And the field of colloidal microhydrodynamics, which looked at the fluid mechanics of colloids, has had an enormous impact on several fields. I can mention only colloidal science, physical chemistry, and rheology. Characteristically, the colloidal science community typically looks at particles that are in the micron range or sub-micron range. The colloidal nano-hydrodynamics field instead looks at particles that have scales in the nanometer range, at least in one dimension. I like the word nano-hydrodynamics as opposed to nanofluidics, because typically in the mind of people, nanofluidics is the field that looks at flows inside nanoscopic channels, so whereby the channels are stationary. Instead, here we are really talking about particles that are suspended in the liquid and they are free to move around. So graphene particles, as you well know, are extremely thin objects. So for me, geometry and mechanics is really very important. The thickness is sub-nanoscopic. So single layer graphene is about 0.3 nanometers. The lateral sizes that can actually be large. So we can talk about typical graphene sheets have a lateral size that can go from 100 nanometers to several microns. For the purpose of this talk, it is also important to emphasize that graphene has a molecularly smooth surface. And this molecular smoothness has a profound influence on the interaction of the liquid with the solid and the fluid mechanics effect. So why do we want to study actually the fluid mechanics of these systems? Well, once I was talking to an industrial researcher from Nobel, and he said something that really impressed me. He said, well, for us industrialists, graphene is just an additive. We just mix it with liquids, and we hope that the performance improves. If it doesn't improve, then we don't use it. Okay. So now, the graphene has extraordinary properties by itself, but the performance of a product that you make with graphene in liquid-based processes depend extraordinarily on the way it is processed, on the dispersion properties of the liquid. So whether the particles are aggregated or not, whether the particles are oriented or not, whether the particles are extended or not, this makes a huge difference in setting the difference between theoretical predictions, theoretical limits, optimal performance, and the real performance. And of course, I'm also interested in the, the scientific driver, which is really understanding the thinness colloidal object that we can devise and we can manufacture, and how it interacts with liquid molecules that have the same size of the thickness of the particle. So the ERC project that I lead on this topic touches several different topics. Today I'm going to focus on orientational dynamics and touch very quickly upon some very brief notions of liquid phase exfoliation. The tools that I'm going to use, that I'm using in my research group, are those of analytical theory, so mathematics, continuum simulations, and molecular dynamic simulations. My focus, really, my interest is actually in the theory, and I use continuum simulation and molecular dynamics really as a tool, really like an experiment, to get data, to develop intuition, and to develop theory. It is really necessary to combine these two simulation approaches, because as we have seen, the graphene particles can actually be pretty large in length, and therefore, if you perform molecular dynamics, you will never know whether the predictions that you have obtained will hold for large particles unless you actually try to match with continuum simulations. So we are going to talk about flow-induced orientation, because it is an enormously important topic in the field of colloids that are anisotropic. So practically all the macroscopic transport properties of fluid, be it effective viscosity, the gas barrier properties, I don't know, percolation properties, electrical conductivity, depend very significantly on the orientation of the particle. Practically, if you know the orientational distribution of the particle, you can calculate the effective viscosity, for instance, quite easily. And the reason is that the particles are very light, and therefore they tend to follow the flow, but they will not orient with the flow in general. Okay, so it is important, when we started with this research, we really wanted to get a baseline on what to expect based on textbook knowledge. So what does textbook knowledge say about plate-like particles in general? So if you take a plate-like particle and you put it in a simple shear flow, so a flow that varies linearly with the distance, okay, in this way, so we have a flow that goes from the left to the right on the top and from the right to the left on the bottom, then this flows has a certain circulation, a certain vorticity. In this case, the vorticity vector is oriented, pointing towards the page, let's say, so clockwise vorticity. So if we put a particle in it and is initially oriented with the flow, well, what we expect is that the particle will rotate in the direction of the vorticity, clockwise. The reason is simple, well, just by intuition, while the flow will shear the flat faces of the particle, leading to a torque, which makes the particle spin. And this intuition is actually exact. So for classical colloids, the particle will rotate in the direction of the vorticity, so clockwise in our simple case. The rotational dynamics is, however, much more tricky, and the equidynamics was explained by Jeffrey more than 100 years ago, who developed a theory that explains the full rotational trajectories, which now I will illustrate through a movie. It's actually a simulation, it's not a movie. So here we have a classical colloid of a given aspect ratio that is quite short in this case. The rotational dynamics is as follows: the particle does rotate, but performs rotational acceleration. So it spends more time oriented in the flow direction and flips quite rapidly when it reaches an orientation perpendicular to the flow direction. This is called the tumbling dynamics, or Jeffrey trajectories from the person who first studied it. So you see that the particle rotates, okay? So in a time average sense, it is oriented to with the flow because it spends more time oriented with the flow, but the particle actually does rotate instantaneously. So we wanted to check whether this holds also for our particle. So for graphene particles, and we set up a molecular dynamics simulation. This was already more than two years and a half ago, which we apply a shear to two parallel walls, okay? And we suspend a graphene particle. We have examined both single layer and double layer graphene. And so this is a simulation in water, and we chose water because it is the liquid that is most characterized in terms of molecular dynamics with respect to the interactions of carbon surfaces with the solvent. So it was for validation purposes, really. So what we have found is something that really has puzzled us for a long time. The particle does not rotate. The graphene particle does not rotate, and actually starting from an orientation that is parallel to the initial streamlines, actually rotates counter to the vorticity direction, so counterclockwise, and then it gets stuck in a sort of hydrodynamic potential well at a relatively small angle with respect to the flow direction, performing small fluctuations due to thermal agitation. So this was a puzzling observation that really, kept us engaged and occupied for almost 3 years. And we really have worked hard to explain the physics of what is going on. I will try to explain a very complex physics in 2 slides, essentially. Difficult, but I will try. So to understand the orientational dynamics, you need to consider the hydrodynamic torque exerted by the fluid on the particle when the particle is oriented in the flow direction and is fixed in space. So it does not rotate. So we imagine hold the particle fixed, okay? So when the particle is oriented in the flow streamlines, and on the flow streamlines, there are 2 components to the torque. One component is obvious and is due to the tangential friction that the fluid exerts on the particle and leads to a clockwise rotation. But there is another component which is absolutely not intuitive, that is due to normal forces. If I have here streamlines that are hitting the particle, well, the streamlines cannot enter through the solid, and therefore they must curve upward. By curving upward, they exert a downward force on the leading edge of the particle, and by symmetry, they will exert an upward force on the trailing edge of the particle. So this force distribution gives rise to a counterclockwise torque, which opposes the component of the torque that we had talked about before. So which one wins? Well, it turns out that for classical colloids, the first component of the torque wins. So it is larger than the second one, but it is larger by a very small amount. That scales like the inverse of the aspect ratio square. And if you account for the fact that typical graphene particles have an aspect ratio of 1,000, you realize that the difference is between these 2 contributions is actually very small. Because the difference is small, just this very small perturbation can alter the dynamics to leading order, so qualitative effects. So we have examined the stress distribution over the particles, and we've done a very complete analysis, and I will just give you an observation that is probably the most important. What we have noticed by looking at the stress distribution in the tangential direction is that the stress over the flat surface of the particle is much less than what we expect initially from the theory. So we have a wall that is oriented in the direction of the flow. So it's like a quad flow, a simple shear flow. So you would expect that the stress is just the viscosity times the ambient shear rate. But actually this estimate is wrong. The MD data say that the stress is actually much smaller than that. The reason why it is much smaller than that is that the solvent molecules do not adhere completely to the solid. So there is a small amount of slip between the solid and the fluid. In other words, using hydrodynamics terminology, there is a slip length which is typically of the order of 10 nanometers or so. We measure 19 nanometers, which seems to be consistent with the literature. There's a wide scattering in the data. So when the postdoc, initially my postdoc Catherine came to me and said, this is the cause, I didn't believe her, because I said, well, 19 nanometers might actually make a difference for a very short, small nanoparticle, but for sure will not make a difference for a colloidal particle that is 1 nanometer thick, but 10 microns in length, right? It's a small error on the boundaries. And she proved me wrong. Another example of the fact that supervisors are very often wrong. So here I plot the torque, dynamic torque versus the inclination of the particle, considering the different cases of a particle with slip or without slip. So the blue line is the particle without slip, so no slip particle, a classical colloid. And the red curves are for graphene, monolayer, or bilayer. You can see that for a no-slip particle, the torque has always the same sign. It's always negative, which means clockwise direction, rotation with our conventional sign. So the particle will never attain a stable orientation. If I include slip, then the entire curve shifts upwards. So there will be regions, angles for which the torque is positive, and angles for which the torque is negative, and there will be a very specific critical angle for which the torque is exactly 0. Using asymptotic analysis, we have found that the slip length, which shifts the curve enough upwards that it crosses the horizontal, the y equal to 0 axis, is of the order of the thickness of the platelet. And this is an important result because, first of all, it does not depend on the length of the particles, since it applies both to short particles and to long particles. And second, this explains why people actually have not noticed this effect before. Because in the classical colloidal science community, people were typically looking at particles that are, have a small slip length, but relatively large thickness, okay? So at least, several tens of nanometers. Instead, by studying graphene, we have uncovered a regime that was not touched upon before, in which the slip length is typically larger than the thickness. We have examined several other combinations based on the literature of solvents and solid. We believe that our results are robust for a wide combination of material properties. For instance, graphene has a large slip length not only with water, which is understandable being carbon essentially, but also with non-polar solvents. Ethanol, for instance, gives a large slip length. NMP, which is considered one of the best solvents for graphene, for dispersing graphene, has a slip length of about 14 nanometers, which is actually quite comparable to that of water. Other 2D nanomaterials seem also to have a significant slip length, smaller than graphene, but still larger than the thickness. For instance, MOS2 with water gives a slip length of 5 nanometers, and boron nitride about 3 nanometers, which is small, but it's still almost 10 times larger than the thickness of the particle. So we believe that pristine, non-functionalized graphene or 2D nanomaterials may display this arrested dynamics. Of course, if you functionalize the basal plane of the particle, you might actually mess up the slip length, and there will be we have found, for instance, that with graphene oxide there will be a threshold surface coverage of the oxygen group beyond which the slip length is reduced below the threshold limit. I was fortunate enough to present my results to Jean-Marie Leng, Nobel Prize winner for his work on supermolecular chemistry. And I was surprised I was expecting failure in front of a Nobel Prize winner. Instead, he was actually quite excited about the results because he said that, historically people have been using hydrodynamics to probe the orientation and shape of molecules in general for a long time. So he suggested to look at molecules that are similar to graphene geometrically, but they are not graphene, polycyclic aromatic carbons molecules are an excellent starting point, and suggested to look into coronin, which is essentially benzene rings with the entire molecule is surrounded by hydrogen atoms. So it is essentially nanographene, and is also of interest in some applications. We have tested the theory with this molecule, and the theory seems to work, at least with MD. We don't know in reality, and we are hoping to get experimental confirmation. And we could prove the theory for a wide variety of Peclet numbers, where the Peclet number measure the competition between Brownian motion and viscous forces. So what are the implications of this work? Well, to me, the most important implications is that we can use slip as a modifier to tune the viscosity of a suspension. We have found that there is a very significant reduction in viscosity if the particles are lying with the flow. This is because they dissipate viscous stresses. They dissipate in viscosity much less. Of course, also the particle does not rotate, so it might actually be able to flow in thin nanochannels without getting stuck, and probably solving one of the biggest problems in printing of graphene, which is actually clogging of channels and nanochannels. And one might also envision ways of measuring the slip properties of graphene or other colloidal systems by using the theory to perform neurological measurements and backing out the slip length, or by measuring directly orientation to scattering experiments, for instance, and getting the slip length. So I see that I'm running a little bit late, so I will try to wrap up a couple of slides. So another topic that we have considered is the shear exfoliation of graphene. And one of our questions was, what is the shear rate that one needs to apply to a mixer in a liquid exfoliation process to delaminate graphene layers to produce graphene. So in liquid phase exfoliation, you just disperse graphite particles in a solvent and you apply mixing. How can you calculate the shear rate? How does it depend on the parameters of the particle and the solvent? If this question could be answered, we could design solvent design strategies that improve dispersion properties, and we could produce high quality graphene in large quantities. And we have developed two classes of models which seem to give results that are quite close to experimental or MD data. So if you're interested in these details, please read the papers, and I will be also happy to share them with you, or just contact me if you are interested in the topic. Just one last comment. What is the big challenge that I have found in my project? I would say the very poor quality of current data on the flow processing of graphene. So the experimental community has focused on proving the materials, the graphene as a material is very beneficial and can give wonderful performances. But the performance is, in many cases, largely dictated by dispersion processes. And the quality and quantity of the experimental data that is available is not sufficient to develop a complete theory. I think we also have a responsibility as a theory and simulation community to help the experimental community by providing testable predictions, which means predictions that can be directly related to experimental observables. And given that we are talking about nanoparticles, probably these observables must be statistical observables. So macroscopic quantities that can be measured directly with large numbers of particles. With this, I would like to conclude, and I would like particularly to thank support from the ERC, and my wonderful postdocs, particularly Catherine and Simon, who are really responsible for the CONTINUUM and the MD part of this work. Thank you.
Thank you very much, Lorenzo. That was great. Anybody have any questions? If you'd like to raise your hand in the chat or unmute your microphone and just ask away, that would be good.
I have a question.
Thanks, Carla. Go ahead.
So I want to ask about the condition of the molecular dynamics. Do you use thermostat or biostat, and if so, do this condition influence the behavior of the graphene flakes?
I have talked quite extensively with my postdoc, and so the information that he has given me is that he has considered both thermostats that are applied to the walls and thermostats that are applied directly to the solvent, and he opted for a Berentzen thermostat since he didn't see major differences in the effect. So the effect is not, I would say it's very robust because the slip length is evidently large. You can see it from directly from, let me show you to share again the screen. Do you actually see my slides or you see me?
We have your slides.
You got my slides. Yeah. So you can see that the velocity does not satisfy the boundary conditions very well from this image. So regarding water, because we have plenty of validation data and previous work done, particularly on flowing nanochannels, we are quite confident about the results, as much as one can be confident about classical molecular dynamics. We have used very established 4 fields. We are actively exploring other solvents such as NMP, which I mentioned before. For those, we are less confident simply because of there is very little literature information on interaction between graphene and solvents which are not water. That is what I can say. So does this satisfy you, Carla?
Yeah, thanks. Yeah, that's fine. Thank you.
Thank you both.
If you have specific questions, I will definitely forward them to to the expert of my group.
Okay, thank you.
Devis, if you'd like to unmute your microphone, you have a question.
So can you hear me?
Yes.
Yeah, so I just have a curiosity for Lorenzo that I've noticed in his MD simulations of the graphene in water. There was absence of water inside the carbon nanotube. Even if it's not relevant for this project, I wonder if you noticed the presence of water inside these 2D materials, because it has been a subject of a lot of debate.
Simulations, no. So the simulations that I showed, or at least I'm 100% sure that water does not intercalate in the simulations in which we consider the layers as rigid.
Mm-hmm.
I will ask my postdoc whether he has noticed anything different in the case where we allow the degrees of freedom of the graphene layers to move around, which is something that we did only very recently because we started studying this coroning, and for coroning we have actually allowed the flexibility of the molecule. But yeah, I can say quite confidently that using our force fields and using our approach, which are actually quite standard. My postdoc did his PhD with Frédéric Bouquet and Lorenzo Botto, or I've done actually quite a lot of work on graphene water interactions. So I'm pretty confident that his science is solid, but we did not notice intercalation. And this is actually quite interesting for me because this effect, one of my big questions related to liquid phase exfoliation is how it is possible that a solvent can change the addition properties of between layers of two-dimensional materials if the solvent cannot wet the interior of the multilayer. And this has been a subject of quite endless discussion because many people claim very strong effects of the solvent, and because we see the problem from the point of view of mechanics, I just don't understand how that is possible. If it is a topic that is of large interest to me because, well, if the liquid enters inside the layers, then actually the kinetics of permeation would be very important, and this is something that I have the ability to tackle, essentially, just because of my background.
Thank you, Lorenzo.